Hello, everybody. Here we are again. Yes, we didn't do one yesterday. I know the million people who are looking forward to our live session are totally disappointed. But Sundays usually we're not, even though we worked, we didn't record because we actually took some break and had some fun playing billiards and re, 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 how do you say, researching the particle model because you got those big particles going out after each other and hitting and colliding. Anyways, our first thing we talk about is what we did today. I did a couple of things. I got a fractal from Lori Gardi, who is a good friend from our CNPS, that is the organization, the Chappelle Natural Philosophy Society. And I talked about infinity, and the fractal is a good way of talking about the diversity in the universe through the infinite levels. That was something I'm writing in the book. So I got her to send me what was her favorite fractal because she generates these things. A really beautiful fractal, the red something. I can't remember what the name is, but it'll be in the book. And I made a diagram with it and put it in the book. I also worked on a bunch of graphics for the Denew effect, that is the underwater experiments. I actually did diagrams for the underwater experiments explaining how flows together when they're actually going in opposite directions. When they come together, they actually reinforce and cause attraction, and when they go opposite, they cause confusion and contusions and cause repulsion, and collisions cause repulsion. So I did that, and I'm also writing a few things. And I started writing. I had to write part of the Denew hack, which we call Borkert and Denew. The hack 2 was a Newton-Lesage hack 1, Borkert and Denew hack 2, and then de Hilstrom to Hilster hack 3. So that's what I did. I also did some writing on the same thing, not only the diagrams, and I also put in the part 2 of the book uh, where I started to write in these words, which I think are really interesting. Everything in part 2 of this book is wrong. That's the first sentence of the book, and that's talking about Newton and Lesage and Borkert and Denew. So anyways, I'm not sure I'll keep that for the whole hack, but maybe for hack 3 for you and my part, right?
Oh,
But
especially.
but that's what I did today. So a lot of graphics. So what did you do today, Dad?
Well, I started to add the third part of the section or chapter on anomalies, and I think a couple of days ago we had a discussion about the Allais anomalies and and what was going on there, and especially that, or was that yesterday? Yeah, that was 2 days ago, where they had that transition in the middle of
Yes.
the eclipse that correlated with the rings, or seems to. And so I had already done the Allais, and so I think Sunday, yesterday, when we didn't tape, I worked on the Wang part. I made sure I got the figures in and the explanation in for the Wang. And so this morning I started on the third part, which is actually not so much an anomaly, but it's a related issue to the because these things involve bending of G1 particles. There was the issue of general relativity, where Einstein had predicted a bending of light, because if gravity will bend any object, surely a photon or an electromagnetic wave or even a packet of energy is something. If gravity can bend objects, it ought to be able to bend light. That's one of the statements he made to make the point simple. And the bending of light coincident with the bending of G1 particles that are part of the G1 particle field. So there's other than light out there that can be bent, and that's what I was describing in the Allais anomaly, And the Wang anomaly is the fact that the random G1 particles that ultimately cause gravity can be bent as well if they pass through the corona of the sun. And so that reminded me of Eddington in 1919, where he claimed he proved that Einstein was right. Einstein made a prediction, gravity bends light, and that relates to the bending of the G1 particle that we do in the other anomaly. So this is an anomaly, but it's kind of a related issue. You got only G1 particles out there, some light, some a random field, and we can now see the effect of both. But this morning I realized I didn't quite have this all together in my head, and I spent a couple of hours reading and watching videos. I watched one video by Ed Dowdy. And
Tell us about Ed Dowdy's work, because that's going to be our discussion point today. For those who are interested and may have questions, this is a very interesting conversation about what we've had numerous times, but because we're having to put it in the book, we're having to really put the pedal to the metal, as we say, and really decide. But the question is that, of course, Einstein predicted and became famous for his prediction that space-time, I don't think he called it that at that time, that light is bent by gravity. And of course, Eddington supposedly proved that. It's a little bit, it's a little hard, how do you say, it's a little suspect, his data, and that's been coming and going. But another person who talks about that in the modern sense and says, no, gravity, in fact, does not have a direct effect on light. He calls it indirect effect, is Ed Dowdy. So since you watched him, I want to have my dad tell you about Ed Dowdy, because we know about Einstein.
Yeah, let's scroll. Can you display this or not, or do I just have to...
Display what?
I got the pictures in the book. Number one is a very interesting picture of one of the photographs of what Eddington, the one, you told me there were 16. I found one of the photographs of the bending of light from a star behind the eclipse that came around.
What did you call it? Did you put it in the...
Well, no. Oh, you got to...
no, but what's it called? I don't see Eddington here. That's okay.
1919. Dad graphics, right up front.
Oh, okay.
One of the first ones.
Oh, okay. Okay, let's see. If I can somehow get this.
Well, it shows pretty well in the book.
Yeah. Well, it doesn't show super well here. Let me see if I can grab it and make it go bigger in this thing here. Yeah, we should have prepared for that. But while you're talking, why don't you talk about it? I'm going to see if I can do it. I can't get this bigger.
Okay, well...
Go ahead, talk.
Well, there's a couple of things that Ed Dowdy has done. First of all, he's a NASA scientist. And in the video I watched, he had a YAG laser.
Well, what's this here we're looking at here?
Oh, I'm sorry, you got it.
Yeah.
No, that's a photograph of the eclipse. This is a picture during the day. This is daylight. Normally the sky is blue, even when you watch an eclipse. But this isn't what you have here. What you have is, I think, an interval of time where they took, they opened the shutter to a plate and took a picture for a period of time.
Of the star? This is the star, isn't it?
No, that middle one is the moon and the sun. And you're not seeing the eclipse. What you're seeing is there's enough light over a short period of time coming from the moon and the sun that it blotted it out and makes it look like a sun only. But that's an eclipse, because over here where the red mark is where they claim the light is the if you're standing here like right straight in front and you're looking out this way, you're seeing the star way back there when in fact it's physically back behind here. Okay. But at first you have to say, well, wait a minute, this doesn't look like an eclipse. I don't see the moon, I don't see the sun. It looks crazy, but
Was there another one?
no, that's the only one I found.
Okay.
Now there is the stuff that Ed Dowdy did. If you go to D, it starts with Dowdy. There's 3 of them.
Okay.
You want to do the well, I don't know, not that one first. That one.
Okay.
I think that one.
Okay.
This is the one that we've seen. You and I have seen this one over and over again, and he talks about the fact that during the what I call the corona, he calls it the plasma rim of the sun, is that light yellow spot around the sun, and when the light from the distant star comes through, it bends in, or if it comes this way, it bends in. But once it gets past this radius, it goes straight. Okay, but this is just a drawing. It's not proof of anything. It's just his drawing of what happens. But that's what he's saying. What he's really saying, and it's not shown in this picture, is that if gravity really is bending the light, then it should bend here too.
Right. Yeah.
And it should bend there too.
Sure.
Okay.
Sure.
And so what? This triggered me right off the bat. It says this is observed. Well, I don't believe this is from observed light. The observed part comes from the what's called the Einstein Ring. Okay, when you visualize, and I don't have the picture here of the ring. I'm sorry, but when you have an eclipse and it's a full eclipse, you oftentimes get a real clear ring around the sun and the moon during the eclipse. Plus, as it just enters, just before it becomes a full eclipse, moments before this one bright spot comes popping out. Yeah, you've
I mean, everybody's, I think, seen that. Yeah.
Yeah, this bright spot comes popping out, and but you see the whole ring, and that's called Einstein's ring because the white is a round circle, and the one spot that pops out in really intense looks like a diamond. So here we have a diamond ring. They call it the Einstein ring,
but wait a minute, before Dowdy says observed, what he meant was that you see the star where it's supposed to be, right? That's what it's observed.
That's what he implies.
Yes,
but there isn't anybody out there looking.
Well, he must have.
During that eclipse in 1919, there was nobody.
Oh yeah.
Okay, there's nobody way out there able to look and see it straight.
Okay, you meant for during Eddington. Okay.
Yeah, I'm still talking about Eddington. This is what you should have seen, and the way the photograph shows you that the picture I showed you of the plate that was actually from the Royal Society of London. That's not what you see.
Well, that's only from one.
But that's his point. You would normally see this. Now, to prove that it's not happening on the outside of the eclipse. Okay, now I'm going to change outside. I'm going to throw away the eclipse. You go to a night sky, and all you have are stars. Now I did in his video. That's just another picture, but in this video, there's a real neat explanation. That's still the eclipse. There's a neat explanation about you look at a night sky and you got all these stars you can see at night. None of them have Einstein's ring.
Einstein Ring, yeah.
None of them have it. But not all of them might have them. There's no reason why all of them should have it, but there's a special cluster of stars. There's an S. The name of one of them is S2. It has an elliptical orbit around a very dense object, and every time it comes around behind the dense object, he claims it ought to show an Einstein ring, and it doesn't. Okay, so when you're not looking at an eclipse. There's no eclipse around you. Just looking at a place where you should see it. It's not there. So when he says in that one drawing, observed, it's, yeah, something like that. Okay, you're supposed to be able to, I don't know if he is there or not. I can't tell. That's not the same video that I was looking at. So it's really two separate events, and he's drawing the conclusion. Ed Dowdy is drawing the conclusion, and he has access to this information because they stole his YAG, his yttrium argon laser light from him so they could do these experiments. But he was at NASA at the time, and he could see the results, and he's saying, no, you don't see Einstein's ring at any time, even where it's logical they should happen.
Okay, so you're talking about the black hole at the center of the galaxy, and then there's a star going around it. And
Well, I don't talk about the black hole in the center of the galaxy, but
no, I mean, but you're talking about that's what the phenomenon you're talking about.
yeah, that's probably is right. Yeah. I mean, I spent 2 hours looking at this. This doesn't mean I have it all straight and can explain it clearly. So the end result is Ed Dowdy has this video, and I have that in the paper. I put the link to the video in the paper, and I took a couple of pictures, and I probably should take some more. I haven't really finished that part. Mm-hmm. I'm a little bit. I need to let it. I may come back to it by the Wednesday or something, when it's settled in, and I get a fresh look at it. But the whole point was, he's constantly saying that this situation that you have with no Einstein rings out in normal night sky is proof that it doesn't happen out there like it might happen with the eclipse. But he also goes through a lot of calculations. He has a chart. There's the chart right there.
No, it's not.
No, that's a different thing.
Yeah.
Well, there's a chart. I have that in the book where he compares the calculations based on gravity, as he understands it, versus general relativity calculating what it should be. And you can see that after it goes a very little distance, there is no bending of light after a very little distance beyond the corona. I'm very picky. Those are calculations. Those are not literal observations that have literal proof. By the way, I made one of my common statements I make in my videos in a book. I don't know how many times I make it. Probably not. I'm making it more in the videos. And the fact is, that plate that shows the bending of, that supposedly shows the bending of light, that's the.
Yeah, I know.
Yeah, that's it. See, it's got three of them here that say if you're close, it's negligible a little bit, but once you're past very little percentage change, it's only a small percentage change. And once you're halfway out, you got nothing. But this is calculated. That's not to me recorded data. Mm-hmm. He generated his own equation based on gravity, and he's saying it won't bend. General relativity says it does. It won't bend. That video, he's constantly saying no. General relativity is wrong over and over again for any number of these reasons. Mm-hmm. But what's in the text of that I put in the book Eddington did that, he has what I call direct evidence of light bending. Assuming he's interpreting the thing correctly, there's direct evidence of light bending. Even Dowdy doesn't dispute that. But that doesn't mean it was gravity at all.
Of course, it's like redshift, right? It's
Doesn't
like
mean it was gravity. If you're a proponent of general relativity, you're going to say, well, it's caused by massive objects cause a gravity well. When light comes by it, it's going to follow the well and bend. That's as simple as it is in general relativity. We take our particle model and we say, no, wait a minute. Physically, there's no way for a G1 particle field to bend light because it's G1 collision on G1 collision. So if you're a proponent of our model, you got to say no. All depends on.
I think there. Well, I mean, yeah. I guess this comes down to the whole thing in our model, which is what, pushing the wrong buttons, folks. Sorry about that. Let's see here. But in our model, we have a physical model for light and a physical model for gravity, and they happen to be the same particle. The only difference between one is just a random field of particles in all directions, and that's gravity. And then light are any streams of particles coming at you in groups in a frequency. And so you can't have its own particle. It doesn't make sense. You can't have a part. This is one of the things that I'm thinking we need to put in the book, just sort of to say, and that is. General relativity assumes that light and gravity are two different particles, or photons and gravitons, for instance.
Well, they're assuming that everything is subject to gravity, whatever it is.
Yeah, but that's sort of not really, because that's why they're trying to put together, in quantum gravity, right? That gravity and the subatomic level. And again, because if you don't have a physicality to all that, it's just like charge and moving electrons, and do they cause fields or do they not, and all that stuff. It's just because they don't have a model, so they're going to be lost.
I made an interesting statement in our book that in our particle model, G1 gravity works on atoms, molecules, and larger. So if G1s are going to bend light has to be at least an atom. That's a conclusion we would draw. Light has to be an atom or a molecule or something bigger, and then gravity could bend it.
And the problem with all that is you come back to the same thing, which is whenever I'm doubting the model, but when I do have, when we think about our model and says, is this real? Is this right? One of the things I always come back to is, well, if things travel at the speed of light, it's really hard to say that those things are different particles. It's really tough. I mean, how would you move different masses and happen to move them all at the same? If photons and gravitons are different particles, then how are they moving at the speed of light? Because we know, even I think mainstream, if you look it up, mainstream science, I think in general says that gravity is traveling at the speed of light.
Yeah.
And of course the Wang eclipse.
There was the real proof was the Chinese that did that study of gravity, the speed of gravity, and they did it from the moon, not from the sun, which is amazing. And there was a report back out, and I think they did the experiment in 2012, and there was a report in a Chinese science newsletter in January of 2013 that reported, yes, they found that gravity was the speed of light, and they had measured data and a theory put together. I read the report.
Yeah, we need to have that reference.
I read
in our
it
book,
once, and I don't know if we should be able to find it again.
Yeah.
But there's sort of there's the to me the Wang eclipse and the LA anomalies. When I woke up in 2008 in the middle of the night saying, it's not about the pendulum, it's not about the bumps in the Wang eclipse, it's about the timeline. And that's when I realized that you were seeing gravitational effects and visual effects of an eclipse at or about the same time. Not necessarily precisely. I don't think you could ever calculate and use those graphs to calculate the precise value. I don't think the accuracy is good enough. But it gave me the notion, yeah, they're both the same speed. And that later I became convinced that no matter what the speed of light is, or gravity, as long as they're the same, Newton's equation works. Newton thought the speed of light was instantaneous and the speed of gravity was instantaneous. They used his equation and were very happy because it all worked out. If it's only half the speed of gravity, speed of light and the speed of gravity is half c, it'll still work. The only difference is, Dave, the spacing between the physical sun and the real sun changes. If it's half c, it's going to be 4 degrees. At c, it's 2, and then it exponentially gets closer and closer. So as long as they're both the same, you can, I'm sure the cosmologists today use Newton's equation. They figure out where it is. They use the distance and what they know about the mass to calculate the forces, and they all do it as if it was instantaneous.
Oh yeah,
and it all works. So they're using that concept of instantaneous speed of light. And
well, they're
gravity.
using two things that are wrong, but it works because it doesn't matter. One is it's instantaneous. Two, that it's a sphere.
Yeah.
So
well, in the long distance, it's pretty much
you're right.
To be a point.
And exactly. So it's sort of like fractals. You're going to be dealing at a level, and if that level and those equations work fine, and that's why Newton's equations work fine and the gravity equations. But they do take into account, I think 4,000 or 5,000 objects in the solar system. So they have a program that they're constantly tweaking. And I think what they do is they look at observations in the sky, and then they will tweak things to put them in the back a little bit, but their model is churning away. So I forget, there's a name for it, and I think everybody has sort of access to it.
But Newton, according to Melbourne Evans, who wrote a paper in 1958, he covered Newton and Newton and something about gravity. It's a two-part paper. It's a great paper, but the last half is about R squared. Newton was convinced that R squared worked for distant objects. Why? One reason maybe they're like point masses, and his equation worked with point masses. He was concerned about the apple, the tree, and the earth, and whether or not his equation properly described that, because the tree is this strange looking thing and the apple's a nice ball, the earth is a nice ball, and does his equation work? Finally, he said he actually believed it did not work below the surface of the earth. And I contend it does if you
yeah,
work
of course
it right.
does. Yeah.
But the whole point was Newton with it. Yeah, Newton and R squared. He wasn't convinced it was universally applicable. We call Newton's equation or it's a universal law of gravitation. It's my opinion. It's not universal, and it's not a law.
Yeah. Well, I think you would agree, though, with what we know today.
I think Newton did a great job. The best thing he did, in my opinion, we get it.
Here it is.
Was when he defined force as an abstract concept of something he didn't know. For example, his gravity equation. He knows that the two objects move together, and his equation talks about there's an attraction by virtue of multiplying the mass over mass divided by r squared. But on the left-hand side, the cause, the force, he didn't know what that was. He would have loved to know what it was, and he could put, like we could put G1 particles or something over there and make it work. He says, but I don't know what it is. So what he did was, whatever gravity is, he condensed it, if you will, down to a magnitude and a direction, a force of magnitude and a force of direction. And that force is defined by the right side of the equation. Coulomb's law, same way. Force, don't know what it is. It's an abstraction of the reality. And Coulomb's law gives you another equation that the magnitude and direction is defined by that other side. If he hadn't have done that, you wouldn't have had force, you wouldn't have had energy, the whole thing. But he abstracted the concept to say, I don't know what it is, I'll make it a magnitude and direction based on what the other part is, what the other thing is doing, not what gravity's doing, but what that's doing. To me, that was genius, because the rest of it was able to be worked. Otherwise, what would you do?
Yeah, it was probably hard for him, because he's probably saying, well, I want to know what this is, but now I'm really going to generalize it, because he just didn't have take the step that people later after him did, including ourselves and other people. But
I mean, I think that point is missed.
But you then for our movie Einstein Wrong, you came up with an equation that ended up with a curve very similar to Newton's curve, right? And that was doing pretty much, maybe, I think he would have been very excited to look at that, because it basically answered that first question that he had, which is, well, I don't know what it is, so I'm just going to make a basic force. It's sort of like, it's sort of like those arrows you draw. Is that what Newton did? Was that Newton's arrow?
Newton did not invent the arrow.
No, I'm talking about the Bob D. Hilster arrow.
I know what you're talking about, yeah.
Which is, all over the place. Yeah. But, I understand it, but it's an inside joke, folks. I don't even know. I guess we're going to see whether or not the half arrow will make it even to the book.
But
I think it will.
With my equation, and we don't normally talk about equations, I started out by just having a sum, adding up the number of particles. I had this mathematical problem in my head that said, well, if I do that and I do this calculation over all 360, all four or 3 dimensions, I'm going to end up with an answer that has 5.235 particles.
Right.
Or 5,000, and I'm going to have fraction of particles, and I didn't like that. I even thought of integer math. I said, maybe I should use integer math. And I said, no, I don't like that either. So instead, I invented a new term called the instantaneous force of gravity, caused by one particle hitting one part of the object. Called it F sub I, instantaneous force. And I used it as a sum so I could have force, an abstract value and direction based on the instantaneous value of each one. And then I summed them up all around the objects involved to come up with the answer. Even me, I'd have been stuck if Newton had abstracted force and set up that pattern for people to use. It's one of the most underrated ideas that Newton came up with.
Yeah, well, like I told you at the time, I said you're doing calculations that I don't think anybody's really done before, which is sum up basically you make a gravity made of little particles that hit stuff, and you calculate all those little forces, and you sum them up. And sometimes even on blackboards, even though they're summed up from 0 to 359, you can write wrong numbers and get that wrong, even in famous photographs. But that's an inside joke these
The
people.
photograph I
Since,
can't change.
No, but I changed it. Yeah, we
I
got that.
know, I know. I shouldn't
So
have done that. I shouldn't have
that's
done
all
that.
right. That's all
I
right.
was so embarrassed.
I know it'll live with infinite. It's only infamy because we have that photo of you. So, anyways, what
Well,
are we?
I'm going to try to finish the that summary of Eddington and Newton and Dowdy in a couple of days. There's a couple of parts that I haven't done yet. I have not done the diode and the transistors. I haven't done that yet. I did Lesage, but there's almost nothing. It's almost nothing there. It's almost embarrassing. I almost wanted to put a little bit of more history of the follow-on to Lesage, but it's not a history book. And I mean, for example, I went through the book. I sort of scanned through our book today, and I found that we cover electrolysis twice, once in the appendix, once in Hack 3. And I think having done the Wang eclipse in 3, that the appendix ought to be deleted. Wang,
Yeah. That's fine.
and
Yeah.
so I made a list of some of these things that you and I maybe could sit down for about 15 minutes at the most, go over it, make a few decisions, and I can go through and make simple changes because some of them are rather easy to do. So it'll
Yeah.
be, I need to start the semiconductors because they're not
Yeah.
there at all.
Today's Monday, man. I've just got so much to do. I need to. Um, I'm pretty sure I'll be done with the Deneau effect. It's pretty much done. I am trying to keep things to the bare bones of talking about it. When I talk about it as a phenomenon, phenomena. I just talk about that. I don't explain anything very much. I said these are the rules, and then in the Deneau hack, I actually talk about an underwater experiment and say that it's a little different from ours.
Yeah, I think that's the right.
Yeah.
Foundation versus hack.
Yeah, and then the next thing I need to do is sort of the visuals for, light. I already made them, but it was in a different graphics program, so I'm gonna probably have to redo them unless I think they look good. But I probably will end up redoing almost all of those, and I'll sort of rip through those. But the idea is transparency. Opaqueness,
or translucent. Some.
I mean, basically,
I'm leaving that one up to you.
yeah, but I mean, they're just you can do this with diagrams, and that's the thing is you don't really need to explain it too much. You have the picture. Basically, you have waves of particles coming in, but because they'll take opaque stuff, they get so changed on their path. By the time any of them get out, there's no
cohesion,
yeah,
coherence.
Whereas if you have a constant pushing on the like gravity, it's a different story because it doesn't matter. It's just the constant push. In fact, the light itself could just be end up being gravitational, but it's so small compared to the gravity push. So, anyways, I got to do all those diagrams, and then the last part I see is going to be the electronics. So I'm hoping I can really go through these things real fast because then I think what we'll need to do, and I may just do that. I may skip some of the other stuff, which is easier, which is the light stuff, which I've already done, and I need to just redo. Maybe concentrate since we have really. I'm 24/7 on this for a week. Is to do the electronic stuff, like start with a battery and really work on that diagram of what a battery is. Because, from the little particles and, how it's really working with the G1 particles. So I will put that together and then the idea is for us to put together the electronic components in a visual way. So a person can look at a battery and go, oh, that's what a battery does. I mean, that's the idea.
Well, there's, unfortunately, maybe I jumped the gun here.
Oh, no.
Yes, there's I think I may have jumped you on that one.
Oh, you mean you already did it for me?
Well, I did something.
His graphics are really good.
I didn't do the graphics any different than what I do graphics, right? But there's text and discussion.
Oh, no, I expect that to be there. But what
Okay.
I expect is I'm going to draw this stuff
Okay.
so that what happens
Yeah,
is
you're
when
gonna look
people
at it.
see it, they're going to have an intuition for it and not just see arrows and say, what the heck is
I
that?
only did four: the battery, the resistor, the capacitor, and the inductor.
Hmm.
I don't think we need to introduce the transistor in that way. The transistor and the diode's going to have its own section,
Sure.
and by that time, I mean,
Well, I need to build the building block pictures like keys. One of them's supposed to be a copper wire with G1s going through it. Another one will be a battery because a battery is sort of, the engine, right?
oh yeah,
of 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 electronic circuits, and then a resistor, which is pretty easy. So that when we get to these, we can put these things on top of at least the first diagram, so that when they get to the other ones, maybe
yeah.
as you go through the book, you can have
I
less
do
of
the
them.
four circuits. You do the figures, and then after you do with the four drawings. I mean, then you can use those drawings and put it on my circuits.
Right.
And I have an RC, battery resistor circuit, an RC circuit, and an RL. So there's three circuits, and those are all there. After that is supposed to be the diode and the transistor.
Right. So I'd like to get those done because there's so much to do, that I would like to get what I would like to do is at the end of this week of this push, this write-a-thon and graphic-a-thon, is to pretty much have the vocabulary of everything and the way to draw things. And I'm pretty good with that because I'm using the Adobe Illustrator. So I'm getting how do you say, the way these things are drawn are the same. So if I get all the components, done, like the key done, then the rest is just basically taking it and making each one, right? So that's something that needs to be done, and then we have to do the same. I think I need to do the same thing with light, but I can do that one because light has a similar thing going on. But the difference with the light, like with dispersion, where you go from white light to the rainbow, is that we're dealing with waves instead of just G1s going.
Yeah, like my straight lines I had in the triangular prism I picked up off the
Right.
internet. Light comes in and it splits and it's a straight line. Well, it's not a straight continuous row of G1s. It's has to have its pattern.
Right. So
Or I mean, if you can, if you can fit it in, and I do. Most people just do it by color, solid line, like I did. But you can make it a little bit more directed towards the model itself.
right. Right. So okay, we've gone 40 minutes. That's plenty. So Farouk, thanks for dropping by, and all those people are watching this afterwards today. I'm not so babbling and off on things, but it's pretty interesting. We are making great progress, so let's go forward, and we'll have another video. Remember to subscribe to our YouTube channel. Let's see here. We can put those up. This is to our YouTube, principiamathematica.com. We also have Facebook, the principiamathematica2.com. Those things will take you to the Facebook and the YouTube pages. Of course, you can see my dad, YouTube at .particle.guru, which I think these people are driving people nuts or away, or to your YouTube channel. And I have YouTube, dissidentscience.com, which I do promise to have a new one out this week. I do have one I have to redo because of the microphone. You can't already see it. It sort of like blends in here. But hopefully we'll have one going out. And I want to thank everybody for the support and appreciate those listening in. Any comments or questions, let us know. Alrighty, folks. We have to have say goodnight, Dad.
Good night, Dad.
Yep, I knew you'd say that.
What's this? Say good night, Gracie.
No, it was
George Burns and Gracie Allen did that.
Boy, that was in your generation. Mine, when I was growing up, it was the laugh-in. Good night, say good night, Dick, and he'd say good night, Dick. Yeah, so it was a
They
laugh-in.
stole it from George Burns and Gracie Allen.
And we stole
Come
it
on,
from
see,
them.
you old guys listen, remember that.
Good night, Dad.
Good night, Dick.
I'm Dave. I'm
Well,
Dave, he's Bob. And we are the particle model gurus. Yeah, no. We'll see if it's guru or not, folks. You'll be the judge when the book comes out. Ciao for now.
bye.